So students, our next chapter is current electricity. In the previous chapter, you studied about the properties of charges at rest, the electric field, the electric current, that is, the electrostatic current constituted by the charges and the electrostatic force. Now, in this chapter, we will study about the properties of charges in motion. And you had already studied in your 10th class that the rate of flow of charge carrier is known as the electric current, the current which is flowing in our appliances. So, electric current is the flow of electric charges through a conductor, and that current is equals to the flow of charge, that is charge flowing through a conductor in a unit time, and the duration of time is very small. So this is our instantaneous current for a particular instant of time. For a steady current, we can say that electric current is total charge flowing through a circuit or a conductor in a given time. The SI unit of electric current is ampere, and 1 ampere is 1 coulomb per second. So we can define, if 1 coulomb of charge crosses a unit area of a conductor in 1 second, then current through that conductor is said to be 1 ampere. So ampere is SI unit. Apart from ampere, other unit also exist, that is milliampere equals to 10 raised to power minus 3 ampere, microampere equals to 10 raised to power minus 6 ampere. And there are some values of current we are using in our day-to-day life, like in our domestic appliances, nearly 1 ampere of current is being used. A lightning during thunderstorm contains a current of order of 10 raised to power 4 ampere. And in our nerves also, you know that electrical signal is being flowing, so that electrical signal is of the order of 1 microampere, that is 10 raised to power minus 6 ampere. And you know that different organs convert these signals into this electrical signal that is being identify our brain. Okay. And you also know that the current is of two type. One is conventional current, and that is electronic current. Now what is conventional current? In a given circuit, we consider the flow of current in a particular direction. So in outer circuit, when we are drawing a circuit diagram, conventional current shows the flow of current. So this is the flow of current, this arrow shows. Now what happens in case of electronic current? Electronic current is basically because of the flow of charge carrier, and we know that current is nothing but the flow of charge carrier. So in which direction the electrons are moving, current is actually moving in that particular direction. So this is the direction of flow of electron, and this is the direction of flow of electronic current inside that circuit. But outside we use the direction opposite to this electronic current direction. Why we are using this? Because the direction of current was identified or being given before the discovery of electrons. So that's why we are considering that the direction of flow of current is opposite to the direction of flow of electron. Now, electric current is a scalar quantity, although it is having direction. So the electric current is having magnitude, and we specify direction also, that the current is flowing in this particular direction, either left or right in a particular circuit. But although having direction, the current is a scalar quantity. Why it is a scalar quantity? because it is additive in nature. For a given circuit, the current at a junction will be the sum of the current flowing through different conducting wires. That is, at a junction, the current will be the sum of all the currents. Now, how that current flow in a given circuit and how to maintain a steady current in a circuit. How can you maintain? Students, you know that in order to get a flow of current in a circuit, we need to maintain a potential difference. If there is no potential difference in a circuit, it is not possible to get current out of that circuit. So how to maintain that? Potential difference means one terminal is at a high potential, another one is at a low potential. So we can obtain this by attaching a cell or a battery to a given conducting wire. So this R represents our conductor having a resistance R, and a battery is being connected to this. Now after the battery or cell is being connected, the current is flowing through this circuit and this appliance start working. Now as it is given in this circuit, this is positive terminal which is at high potential, this is the negative terminal which is at low potential, and you can see that the current is flowing from positive to the negative terminal. These arrow shows the direction of flow of current. So from high potential to the low potential. But actually the current is flowing because the negative charges are moving from this negative to positive terminal. So now you can see from this circuit that this arrow shows the direction of conventional current, but actually the electric current is from this negative to positive terminal, that is the opposite to the flow of the conventional current. That is because of the movement of charge carriers. And this outer shows that the charge carriers are moving from positive to negative, but actually they are moving from negative to positive inside this. Now you can think of a water tank which is at a height and which is having a very high level of water in it, and there is another water tank in which we are having low water level. Now what is happening here? The water is being pumped here from here, and from this high it is being falling down and filling this. Again what is happening? We are pumping this, and again, so what is happening over here? We are maintaining a steady flow of water out of this high potential water tank to this lower potential, and this is what is happening here only. So we are getting a steady flow of current. Now what is electromotive force? Now whenever a cell or battery is being connected, we get a flow of current through that particular circuit. Let us consider a case that we are having a cell, okay, and A is the positive terminal, B is the negative terminal. Now due to the opposite charges, there will be movement of charges, and suppose Fe is the force with which the charges are moving towards this place, means this is applying force. A is applying force on B and B is applying force on A. Now Fe is the force due to electron and Fn is the force due to the positive charges, and there is a separation D between these two terminals, positive and negative terminal. When we are having the steady state, and we know that because of the conservation of charges, the two forces will be equal. So Fn is equals to Fe. Now what if we are making the charges moving from B to A? That is, electrons are being transferred from B to A. In that case, what will be the work done? Work done will be force into the separation. Now Fn is the force with which the electrons are being traveling from plate B to A, and they are covering a distance d. So the work done will be Fn into d, and what will be the work done per unit charge? That will be work done per unit charge is force into displacement upon this. Now we know that work done per unit charge is what? The potential. Here we are considering this as E. Now what is this E? This E is the electromotive force or EMF of the battery. Now what is this EMF? EMF is defined as the work done by the source in taking a unit positive charge from lower to the higher terminal. That is, from this lower to the higher terminal. Now we are saying this, it is electromotive force. Is it a kind of force? And here we are saying that it is potential. Now why we are considering it potential and why we are saying that it is a force? So basically some force is required in order to make the charges move from one point to another point. But with that force, some potential is being developed. So that's why this is the potential, and for a given circuit, this is the highest potential. Now, we are saying that if these two terminals of the battery, that is A and B, are not connected to external source, in that case, the two forces will be equal, and that will be the charge and the electric field between the terminals. So we can say that FND and FED is equals to Q into E, that is the force, into D. Now this is the work done. So what we are saying here, that the work done in moving the charges from the negative to positive plate is equals to the work done moving the positive charges from positive plate to the negative plate, and that comes out to be charge into potential, because we know that E into D is potential. Now we can say that our electromotive force is equals to force into displacement upon charge. Substituting this value from here, we are getting Q into V upon Q, and that is equals to V. Hence what we can say, that the electromotive force of a source is equal to the maximum potential difference between its terminal when it is in open circuit. Here what we are saying, that the terminals are not connected to any external source. We are not connected anything, that is, no conductor, no wire is being connected to this battery. So in that case, our EMF is equals to the potential difference between the two terminals, and this is the maximum potential difference. And students, whenever we are connecting any conducting wire to that, this maximum potential difference reduces, or we can say that EMF reduces. Why it is so? Because the conducting wire is now being drawing some current out of that. It needs some potential in order to maintain the current flow in the circuits. That's why EMF is the maximum potential difference in open circuit. Remember this thing always. Now let us consider a case of an electrolyte. So we are having an electrolyte in a container. We are having two electrodes, one is positive, another one is negative, inserted in this electrolyte. Now what is happening? And this is our basic cell, and this is a symbol of cell. So we are having this conductor. It is being attached to these electrode, positive terminal and the negative terminal are being connected here, and this is the electrolytic solution. Now what is happening? The potential over here at plate P or at electrode positive minus the potential nearby this, that is the potential of this electrolyte near to this positive plate. The difference of these two, that is the potential difference of this positive rod and this electrolyte near to this, comes out to be positive, that is V plus, and which is greater than 0. And if we are considering the case of this negative electrode, in that case the difference of this negative electrode and the electrolytic solution which is nearby this electrode, it comes out to be negative, that is less than 0. Why it is so? Because in a steady state, the potential of this whole electrolyte is same. Depending upon the polarity of the electrode, the difference over here or the net resultant potential over here is positive and over here it is negative. Now when we are adding these two, in order to get the net EMF, V plus minus V minus, that is, this is the negative, this is positive, what we are getting, the resultant is positive, V plus V minus, that is EMF of the cell. So we can say that the net resultant potential difference for this cell is always positive, that is the greater than 0. Now what is SI unit of this EMF? The SI unit of this EMF is volt, because this is nothing but the potential difference between the two terminals of a given cell when they are in open stage, that is the circuit is open. So it can be defined as the EMF of a source may be defined as the energy supplied by the source in taking a unit charge once round the complete circuit, from here to here, complete circuit. Now after this EMF and the potential, you know that what is Ohm's law. You are aware of this Ohm's law. You know that under steady conditions, physical circumstances, that is the constant physical circumstances, like the temperature is constant, material of device remains constant, in that case the current flowing through the circuit is directly proportional to the potential difference across the ends of that conductor. Now current is proportional to potential difference, or mathematically we can say that potential difference is proportional to current. Both are same thing. Now it can be written as V is equals to IR. R is the constant of proportionality and known as the resistance of a given conductor. And we can plot a graph for this. This is your potential, this is your current, and we are getting a straight graph. Now the slope of this VI graph gives the resistance. So what is resistance, students? The resistance is property of a conductor by virtue of which it opposes the flow of charge through it. So resistance is a property of a given conductor. Because of this, it opposes the flow of charges. SI unit of this resistance is ohm. And now what is 1 ohm? 1 ohm is V upon I. So what is the unit of potential difference? That is volt. Unit of current is ampere. So SI unit for resistance is 1 ohm. This is symbol for ohm, omega, and this is equals to 1 volt per ampere. Now we are using resistors in our electrical circuits, and you will perform so many experiments in your lab based on these resistors and electrical circuits. So you have to draw the circuit diagram, and for that you need to draw the symbols for resistors as well. So here are few symbols for resistors and meters as well, which we use in our electrical circuits. So the symbol for fixed resistor is this or either this, and we are using this symbol maximum. This is a variable. This arrow shows that our resistor or resistance for a given circuit is varying, and this is the potential divider. This is our symbol for rheostat as well. You had studied in your 10th class. So this is variable resistor. We can vary the potential difference in a given circuit, and hence we can maintain the flow of current through a given circuit. Now these are meters. You are aware of these. This is the voltmeter with positive negative terminal. This is ampere, that is ammeter, ampere meter. This is the galvanometer. Ampere meter measure the current, voltmeter measure the potential difference, and galvanometer shows the direction of flow of current. And this is arrow. This arrow shows the direction of flow of current through a given circuit. Now, after defining the symbols, how to measure the resistance for a given circuit? So this is nothing but the simple circuit diagram for our Ohm's law. For that, what we need? Ohm's law states that V equals to IR. Now, in order to find out the resistance value for this given conductor, let us consider a circuit in which we are having a battery to provide the potential difference through this circuit. Ammeter is used to measure the flow of current through this circuit, and voltmeter is used to measure the potential difference across the terminal of this conductor, terminal 1 and terminal 2. Now, whenever the battery is connected and key is inserted, in that case the current is flowing in this manner. From positive terminal, it moves out and flow through the circuit and reaches the negative terminal. Now, these arrow shows the direction of flow of current. Now, this conductor and voltmeter are always connected in parallel. So, from here what we conclude that voltmeter is always connected parallel to an electrical device. Now, what are the factors which are affecting this resistance of a given conductor? In this circuit, by measuring the value of voltmeter and ammeter, that is potential difference in current, we can plot a graph, and the slope of that graph will give us the value for this resistance. In this manner, we can measure the resistance of a given conducting wire. Now, what are the various factors on which the resistance of a given conductor depends? So, it depends upon the length of the conductor. It depends upon the area of cross section of the conducting wire. It depends upon the nature of the material. Now, from here what we are concluding that resistance is proportional to length, directly proportional. Resistance is inversely proportional to the area of the conductor. So if we increase the length of a given conductor, the resistance of that conductor also increases. If we increasing the area, in that case the resistance is decreasing, and if we decrease the area, in that case the resistance is increases. Let us combine these two. What we are getting? That the resistance is proportional to L upon A, or resistance is equals to a constant, that is the constant of proportionality, into L upon A. Now, what is this constant of proportionality? This constant of proportionality is known as the resistivity or the specific resistance. This is the property of a given conductor which we are using for the resistance or the conducting wire. So, from here what we are concluding? If the length of this conductor is 1 meter and the cross section area is 1 meter square, in that case the resistance is equals to the resistivity, and SI unit for this resistivity is ohm meter, that is omega meter. Resistivity for a given conductor is the property of that particular conductor which remains constant, but we can vary the resistance of a given conductor by varying the length, by varying the area of conductor, or by varying the temperature. So by varying the physical parameters, we can vary the resistance of a given conductor, but we can't vary the resistivity. So that is a constant property, that is the that shows the nature of a particular material. That is, the resistivity of copper cannot be changed, the resistivity of iron cannot be changed, but we can change the resistance of iron or copper respectively. Now, after the resistance, our next topic is current density. Now, what is this current density? Current density is the current flowing through a unit area of a conductor. So, the current density at any point inside a conductor is amount of charge flowing per second through a unit area which is held normal to the direction of flow of the charges, that is the current. So here in this figure we are considering an area A, and this is the direction of flow of current. Now what you are saying, that the direction of this area, that is this vector A, unit vector A, is along current, or we can say that the area is perpendicular to this current. Now what if this area is inclined with this direction of current? In that case, if theta is the angle between the area vector and the current, in that case we are having this formula for the area, that is area is equals to, or area vector is A cos theta, because theta is the angle with this horizontal direction of current. So here area is perpendicular to I, and here area is having inclination with current I. Now we know that current density is current per unit area, and the symbol for current density is J, small j. So J is I upon A. This is the case when we are having the area and the current both are perpendicular to each other, and this is the case when there is some angle between the flowing current and the area vector. So from here I is equals to current density into area into cos theta, and we know that cos theta represents the dot product. So what we are concluding, that current is the dot product of two vectors. One is the current density, another one is the area vector. Now we know that dot product of two vector is a scalar. So from here also we conclude that having direction, the current is a scalar quantity. Now what is the SI unit of current density? Current density is current upon area. So the SI unit of current density is ampere per meter square. Ampere is for current and meter square is for area. Now what is conductance? As we know that resistance is a property which opposes the flow of current, and conductance is something which is helping the flow of current. So the conductance of a conductor is the ease with which electric charges flow through it, and it is equals to the reciprocal of the resistance. Okay, so as we know that resistance opposes and the conductance favors the flow of charges. G is the symbol for the conductance, and from here what we conclude, that conductance is equals to 1 upon resistance. SI unit for resistance is ohm, so the SI unit for the conductance will be ohm meter, and it is also known as mho or Siemens, and the symbol is capital S. Similarly for resistance, the property is resistivity. Here for conductance, the property is conductivity. Now conductivity specify how much the given conductor is being conducting current. Similarly, as for the case of conductance, the conductivity is also the reciprocal of resistivity of a material. So rho represents the resistivity, here sigma represents the conductivity. So sigma is equals to 1 upon rho, or we can say that conductivity is equals to the reciprocal of resistivity. SI unit for Rho, that is the resistivity, was ohm meter, and here the SI unit for conductivity is per ohm per meter, or mho per meter, or Siemens per meter. Now, what are the factors affecting the resistivity? Resistivity is only affected by the temperature, and no other factor defines the resistivity. Now here we can see that the conductivity of a given substance can be increased or decreased by increasing the temperature or decreasing the temperature. Now, after studying the Ohm's law, that we know that Ohm's law states that V equals to IR. Now, what is the vector form of this Ohm's law? We know that potential is equals to electric field into the length through which that electric field is being set up. Let us mark it as equation number 1. Now, from Ohm's law, we also know that V is equals to IR. That is, let us substitute the value of this resistance. So, I into rho L upon A. And both are the potential. So, let us equate these two equations. What we are getting, that EL is equals to I rho L upon A, or E is equals to I into rho upon A, and L both are cancel out. So from here what we are concluding, E is equals to J into rho. Why it is J? Because current upon area is the current density. So E is equals to J into rho. And in vector form we can say that the electric field, strength of electric field through a given circuit is equals to resistivity of the given conductor into the current density through that conductor. And the direction of this current density is same as the direction of the electric field. Or we can say that J is equals to E upon rho, and 1 upon rho is nothing but our conductivity. So this current density is equals to conductivity into the electric field. Now this is the required form of Ohm's law in vector notation. In normal, we are having V equals to R into I. In vector form, the current density is equals to the conductivity into the electric field.